Okay, so now that we've kind of ventured into the land of second derivatives, we can pick up new tools to help us analyze an original graph, an f of x graph, okay? So this one's going to be called the second derivative test. Second derivative test, and specifically for critical points. Critical points, okay? So what is this? So basically, let's start with a graph. So let's say we have a concave down graph. Okay, so this is like down, concave down like a frown, right? So this is concave down, obviously. So that means that our the second derivative is going to be negative, right? And see how here we can identify a local maximum. Okay, so we have this local maximum at which the tangent line is a horizontal. So our f prime is equal to 0, presumably. Okay, and let's say we were going through a problem and we had to find the critical point first of all. So I identified what x value this is at, okay? But then we didn't know what kind of extrema it is or what type, right? We don't really want to do the first derivative test where we plug it. We do sign analysis with the first derivative, and then we have to see whether it goes from positive to negative or negative to positive. So a shortcut we could do is actually, so we already identified that this is a local maximum, right? So another test we could do, the second derivative test, is that if you just plug your critical point value, once you've located it, so once you've located, there we go, a critical point, I'll just abbreviate CP, critical point, we can just plug in x value into your second derivative, okay, into f double prime of x, and then you get if your f double prime of x is negative. If it's negative, like here, we have a concave down part of that graph, right? At least at that point. So that means the point must be at the top of the hill, okay? At the top of the frown, right? So we have a local maximum, okay? And then if you get, on the other hand, if you get that if your f double prime of x is greater than 0, if it's positive, then that means we are at a concave up portion of the graph, which implies that our critical point lies at the bottom of the hill, or bottom of the cup, okay? And that signifies a local minimum. Local minimum. Okay, so let me write it on the next slide, what I just said, as far as like second derivative and stuff. So second derivative test, I'll just write that up here. So second derivative test. Okay, so we said that if you plug in your critical point into f double prime of x, and if you get that f double prime of that value is greater than 0, so if it's positive, then that means we have concave up, which is like this, right? And that means we're at a local minimum. We have a local minimum at that point, okay? If our f double prime of x, it turns out to be less than 0, if it's negative, that means that our graph is concave down at that point, at least, okay? So we're at a local maximum. And if your second derivative turns out to be a 0, that means that the test is inconclusive. Test is inconclusive. It doesn't necessarily mean we don't have an extrema, like a maximum or a minimum. It just means that we can't tell from the second derivative here. Okay, so what we would do when the test is inconclusive is go back to the first derivative test. Which that just means sign analysis, right? With the first derivative, with f prime. Okay, so let's do an example of finding critical points and then applying that second derivative test. So what we're going to do is, like I just said, find critical points and apply the second derivative test that we just learned. The second derivative test. Okay, and here's our function. We have f of x is equal to x cubed minus 12x squared, and then plus 45x, okay? So we have a critical point when our f prime of x is equal to 0 or does not exist, so let's find f prime of x first. So we're going to get a 3x squared from the power rule minus 24x plus a 45, okay? So this is going to be defined for all x, right? There's no place where it could not exist. So what we're going to do is kind of set it equal to 0. So that's going to equal 0, and we can factor things out. So we have a 3 times x squared minus 8x plus a 15. That's equal to 0. So then we have 3 times x minus 5 and an x minus 3. Okay, that works. And then equals 0. So our f prime of x equals 0 is a critical point. There's a critical point when we have that our x is equal to 3 or 5. Okay? So these are our critical points, and now what we can do is apply that second derivative test. So let's do so on the next slide. So first of all, we had the f prime of x, because we're going to need that, right? So f prime of x is equal to a 3x squared, and then minus 24x plus a 45. We found that our critical points are x equals 3 and 5. And if we want to apply the second derivative test, first of all, we have to just find the second derivative. So we're going to do f double prime of x is equal to 6x minus a 24. Okay, so now what we do is plug these guys into here and see what we get, positive or negative numbers. So if f double prime of 3 is equal to 6 times 3 minus 24, that's an 18 minus 24, which is a negative 6, which is a negative number, right? So that means that we have at this point, at x equals 3, our graph is concave down like a frown. Okay, so that means at this critical point, we must have a local maximum. All right, so we have a local maximum, and then let's try the other point. F double prime of 5 is equal to 6 times 5 minus 24, which turns out to be 30 minus 24, which is a positive 6. So this is a positive second derivative, so that means we're at a point where it's concave up, so that means now we have a local minimum. Okay? All right, so let's continue on the next slide. We'll write our conclusions there. So we have at x equals 3, we have a local maximum, okay? And x equals 5, we had a local minimum. And sometimes, we could stop here if that's the problem asked, but sometimes they ask for the actual value of the function at these points. So if you have to find the value of the function, of the original function, that is, our f of x, at these points, we're going to do the following. At these points, ... what we do is just plug it into that original f of x. So f of x was equal to an x cubed, and then minus our 12x squared plus 45x, okay? So if we have to plug those in, that's all we do, is really just plug them in. So f of 3 is equal to 3 to the third minus 12 times 3 squared plus 45 times a 3. And that is going to be equal to a 27 minus 108, and then plus 135. So this is equal to a 54, okay? So f of 3 is equal to 54, and also f of 5, when we plug that one in, we get 5 cubed minus 12 times 5 squared plus 45 times 5. Okay, and then that one is equal to a 125, 5 cubed, minus, and then 12 times 25 is 300, and then we have plus 225, so this is going to be equal to a 50. So f of 5 is equal to 50. So another version of our answer could be that we have f of 3 is equal to 54, which is also the point 3, 54, right? And that was at x equals 3, we had a local maximum, right? So local maximum, and then when we plugged in 5, we got an answer of 50. So this is the point equivalent to the point 5, 50, okay? And then this was a local minimum. Okay, so just in case they ask for the value of the function at those points, like the actual maximum or minimum points, as opposed to the x values or the critical points there, just like the 3 or the 5, this is what you do. You just plug it into the function, you can get the entire point. Okay? Alright, so that's it. That wraps it up for the shape of a graph video. I hope that helps, and good luck on your homework.